Okay, welcome back, everybody. I said I was going to do an extra example, and here it is. Extra examples, just like extra innings. They're so exciting and long. So, the next strong induction example I want to do, we're still doing strong induction, is I want to prove this following interesting claim. And the claim is that f of I is less than 2 to the I for all I greater equal to 1. F to the I less than 2 to the I for all I equals 1. So here's the first question. What the heck is F to the I? Excellent question. So F to the I in general represents the ith Fibonacci number. And so I'm going to say that F0 equals 1. F1 is also equals 1. And then we're going to define F to the I to equal F to the I minus 1 plus F to the I minus 2 for all I greater than equal to 2. Very similar kind of the last example. But this is the definition of the Fibonacci sequence, right? Because if we work this out, right, we get, well, F0 is 1, F1 is 2, F2 is going to be the sum of the two previous, 1 plus 1, which is 2. F3 is the sum of the two previous, so 2 plus 1, which is 3. F4 is the sum of the two previous, which is 3 plus 2, which is 5. F5 sum of the two previous, 8. F6 sum of the two previous, 13. F7 sum of the previous, 21. On and on and on and on and on like that. So this literally is the Fibonacci sequence. This is what it's defined to be. So our claim about this is that for all I greater than equal to 1, AI is less than 2 to the I. There she blows. That's the claim. It doesn't even make any sense. Let's check it out, right? I should have left this on the screen. So we had 1, 1, 2, 3. I'll make a little table here. This will be I, this will be F to the I, this will be 2 raised to the I. 5, 8, 13, that'll be enough. And our I0, this is for 0, 1, 2, 3, 4, 5, 6. So maybe I'll put these in here. So the only question is what the heck's 2 to the I? How does this compare? The way it compares is, well, 2 to the 0 is just 1. So here, 2 to the I is not bigger than F to the I, strictly bigger. But 2 to the 1 is 2, which is strictly bigger than 1. 2 squared is 4, bigger than 2. 2 to the 4th is 8, bigger than 3. 2 to the 5th is 32, bigger than 5. 2 to the 6th is, 2 to the 6th is, what am I doing, 64, bigger than 8. 2 to the 7th is 128, bigger than 13. So not only is it bigger, it's way bigger, right? But anyway, how would we even go about proving this? All right, so the claim is this works for all I. For all I bigger than equal to 1, which we just showed, it looks like it's true. How would you actually prove it is true? Because the weird thing is, if we're trying to use a direct proof here, if we're trying to use a direct proof, we're going to run into an issue. And that is if we just said, like proof, let n be any arbitrary / particular integer greater than or equal to 1. If we started there, or I, well, what's fi? Oh, that's gross. But we don't know. There's no explicit formula that tells us how to calculate fi from I alone. We only know how to calculate fi from the previous terms in the Fibonacci sequence. We don't know how to calculate fi from the 2 previous terms. So the point being, our direct proof kind of goes nowhere. Because to know anything about fi, we need to know stuff about fi minus 1, fi minus 2. But we're not assuming it. We don't know anything about them. But this screams induction, right? Because theoretically, maybe we can use our knowledge of the two previous terms, something about these, to show that Fi is in fact, oh, I want Fi here, I'm sorry, show that Fi is in fact less than 2. So, let's do an aside, try to figure this out, right? Notice that Fi equals Fi minus 1 plus Fi minus 2, right? Fi minus 1 plus Fi minus 2. Let's assume, this is how induction goes, right? Let's assume that claim holds for I minus 1 and I minus 2. What do I mean by that? I mean that Fi minus 1 is less than 2 to the I minus 1, and Fi minus 2 is less than 2 to the I minus 2. Well, if we know that, then this is less than 2 to the I minus 1 plus 2 to the I minus 2. All right? Because Fi minus 1 is less than 2 to the I minus 1, Fi minus 2 is less than 2 to the I minus 2. But then, we can be a little clever here. Notice that 2 to the I minus 2 is certainly less than 2 to the I minus 1. This is less than 2 to the I minus 1 plus 2 to the I minus 1. And then we have 2 copies of 2 to the I minus 1. This is 2 times 2 to the I minus 1, which is 2 to the 1 times 2 to the I minus 1. And if we use our exponent rules, right, because we have a common base, we can add the powers. This is 2 to the 1 plus I minus 1. Well, the 1 and the 1 cancel, so it's just 2 to the I. Bingo, right? If the claim holds for the 2 previous terms, it's also going to hold for Fi. So not only does this scream induction, this screams strong induction, because we need more than just the previous case to prove the next one. We need multiple previous cases. So that's going to be the deal. So I guess the question here then, I guess, is what's the base case all going to be? Let's settle that when we get into it. Where's it going to be right now? So we can't push our problems back too far. Here's a moment of bliss here, though. We have to think about it. All right. Proof. So here's the proof. We're going to say proof by strong induction. I'll say on I this time. Doesn't really matter. We can use whatever letter we want. I mean, actually, theoretically, I guess it's like a computer science variable. Like we could use whole. Like there's no reason to introduce a letter, right? We could have made it a whole name. Like we could have said proof by strong induction on Miranda Cosgrove. Who's Miranda Cosgrove? Oh, sorry, Carly. But anyway, yeah, the proof by strong induction on I. So we're gonna have our base cases, possibly multiple, and we're gonna have our inductive step. And so in the inductive step, right, we want to show that for all I greater than or equal to something, P of 0, yep, sorry, 0, because we had F0 here, P of 0 and P of 1, and all the way out to P of I can be used to show that P of I plus 1 must logically follow. All right. The way to write it in this case is for all I greater than or equal to whatever that number is going to be, if P of K holds for all 0 less than or equal to K less than or equal to I, then P of I plus 1 holds. So if, right, our claim holds for everything up to I plus 1, for everything from 0 to I, it's going to hold for I plus 1. And what's our P of k here? Well, our P of k is fi less than 2 to the I. And so this is f to the I plus 1 less than 2 to the I plus 1. That's the idea. And how do we prove this again on our side? Remember, in our side, our whole idea was to write f to the I plus 1 as f to, well, as the two previous terms. So f to the I plus f to the I minus 1, right? So in order for us to do that, remember, this recursive relation holds for all I greater than or equal to 2. So again, we need, so for this to be true, I plus 1 has to be greater than or equal to 2, right? The index here has to be greater than or equal to 2. Here there's an I, here an I plus 1. So the point is the index on this must be greater than or equal to 2 for this to work. So if I plus 1 has to be greater than or equal to 2. When if I plus 1 is greater than or equal to 2, that means I is greater than or equal to 1. This holds for all I greater than or equal to 1. I'll get new markers this weekend. It'll be fun. Love new markers. So the point is, yeah, so when does this hold for 1? Let's go ahead and try to get into the proof. So the proof, so I'm going to say, we're proving this universal conditional statement. It's an if then. So I'm going to say let I be any integer such that I is bigger than or equal to 1. We're going to be in this case. And now the whole deal is I want to assume that the claim holds for everything less than, everything up to I, and then show it also must hold for I plus 1. So let's assume that the claim holds. So assume that the claim, which is this, that fk is less than 2 to the k for all integer k, such that, remember, we want everything up to I. So we start at 0 here. So we have 0 less than or equal to k less than or equal to I. So now that we have that, once we have that, we're trying to show that f to the I plus 1 is less than 2 to the I plus 1 under this assumption. All right, so how do we do it on the other side? Well, we broke f to the I into the sum of the two previous terms. And we can only do that, or sorry, we broke f to the I plus 1 in some of the two previous terms. And we can only do that if this index here is bigger than or equal to 2, which in our case is going to be. So let's say note, since I is greater than or equal to 1, by adding 1 to both sides, I plus 1 is greater than or equal to 2. Thus, by our recursive formula, f of I plus 1 is going to be greater, or fi plus 1 is going to equal f to the I plus f to the I minus 1. It's the sum of the two previous terms. All right. And this is by formula. But then notice, right, that this has got to be less than 2 to the I plus fi minus 1, since fi is less than 2 to the I by assumption, right? We assumed that for everything between 0 and I, for all k between 0 and I, fk is less than 2 to the k. And so in particular, I is between 0 and I. So f to the I is less than 2 to the I. Actually, I'm going to write that down a little more rigorously. So, but let's try a formula, f to the I plus 1 equals f to the I plus f to the I minus 1. So I'll say note, since I is greater than or equal to 1, which is greater than or equal to 0, 0 is less than or equal to I, which is less than or equal to I, right? Any number is less than or equal to itself. 5 is less than or equal to 5 because it's itself. Hence, by our assumption, f to the I, by our assumption, f to the I is less than 2 to the I. You do the same thing for I minus 1. Further, since I is greater than or equal to 1, by subtracting 1 from both sides, we see that I minus 1 is going to equal to 0. Hence, 0 is less than or equal to I minus 1, less than or equal to 1, or less than or equal to I. Why is that important? Because we're assuming, right? Again, it's the inductive assumption. We are assuming that for all k between 0 and I, for all k between 0 and I, f to the k is less than 2 to the k. So since I minus 1 is between 0 and I, f to the I minus 1 is less than 2 to the I minus 1. And now we have literally everything we need, and we are good. So, yeah, so I'll say then, consider f to the I plus 1. Now here's the part. F to the I plus 1 equals f to the I plus f to the I minus 1, right? By formula. But then that is less than 2 to the I plus f to the I minus 1, since f to the I is less than 2 to the I. And that's less than 2 to the I plus 2 to the I minus 1, since f to the I minus 1 we said is less than f to the 2 to the I minus 1, right? We just said that right now. And then this is less than 2 to the I plus 2 to the I, since 2 to the I minus 1 is less than 2 to the I, right? An extra multiple of 2, an extra power of 2 makes it bigger. And then this just equals 2 times 2 to the I by, I guess, factoring, right? Or really we're just adding by adding, which equals 2 to the 1 times 2 to the I by exponent identity, just saying that 2 to the 1 is 2 itself. And this equals 2 to the I plus 1 by exponentiation rule. Where we have that rule that it consists of a common base, 2 to the 1 times 2 to the I, we can add the exponents. Hence, f to the I plus 1 is less than 2 to the I plus 1. So, under the assumption, right, that f to the k, where is it? F to the k is less than 2 to the k, for all 0 less than k less than I. Under this assumption, right, we can show the next one, I plus 1, at the I plus 1, less than 2 to the I plus 1. So if all the Fibonacci numbers are less than 2 to the I for everything, or over the 2 to the k for everything before f to the I plus 1, then the next Fibonacci number, the claim will also hold. That is the chain reaction. So all we have to do, right, is show that it holds for 2 Fibonacci numbers, right? So, or actually, or the conclusion first. Conclusion. The conclusion says, thus for all integer I greater than or equal to 1, f to the I is integer I. So one thing we need to fill in is this base case right here. So let's talk about the base case.